Hello, welcome back to CL961, Geographical Information Systems. In this lecture I'd like to talk about errors in GIS. And it's an important topic because all GIS will contain errors. Nothing is ever perfect. You need to remember GIS is a model. It's a model of reality. And we can only make our model as complicated as we can. So for some things our model might not be complicated enough. So it really depends on the application to see whether or not this error matters. Let's look at some classic errors in maps. This is Sandy Island here on the ocean. This is to the east of Australia. This was mapped by Captain Cook in 1774, and he mapped it as a large sandy island. But there probably never was an island, or it definitely isn't here. It's been on maps for centuries, but in 2012 a research vessel sailed past there and noticed that this island, which was on the map, doesn't actually exist. So if you see a published map, that's no guarantee of its quality. Don't just believe a map because it's published. Here's another example of a map where I wasn't all that impressed. Of course, it's the sun. But what you can see here is the cases of coronavirus last week. And this map, if you look at the color scale, is rather weird. It pays a lot of attention to the small numbers of cases, but then for anything more than 1,000, it uses the same color. And it's a bit confusing. It's not necessarily wrong, but it is confusing to see that Italy has the same color as France, whereas Italy has almost 10,000 cases more. And also, it doesn't consider the size of the country. It would probably be much more representative to look at the number of cases per capita. So if you divide the number of cases by the country's population, because now on a map like this, Luxembourg will always look just fine compared to its bigger neighbors. Whereas in reality it could be much worse. In this example you see two geology maps. One on the left hand side created by the USGS, and one on the right hand side created by the Utah State Geological Survey. So that's the Federal Geological Survey versus the State Geological Survey. And as you can see, even though they mapped the same or neighboring areas on the same scale, they've made different interpretations and the maps don't line up. This area, for example, here, there's clearly a problem here. And there's some smaller mismatches here and there as well. So maps are only models. Maps are only are the ideas that people have about reality, and they try to represent them. So maps aren't necessarily an objective truth. So what is data quality? What really matters? Well, it matters. What matters for errors and for how good your map or your GIS project is whether or not it's fit for purpose. So if you want to record, for example, property ownership, so which part of the land belongs to which person, then you need that to record that in great accuracy. Really, we need sub-meter accuracy, ideally sort of centimeter level accuracy in our positioning and in our recording in the GIS. If, for example, you're dealing with plate tectonics, then millimeters or centimeter accuracy is probably completely irrelevant, because you're talking about a phenomenon which occurs on the thousands of kilometers scale. So recording it to a kilometer accuracy is probably good enough. So it really depends on the purpose what's good enough. Here's another example. This is a highway map, the map to navigate the roads. In this case it's a Dutch example. I couldn't find any English examples, but this is a map that Dutch people use to drive from their home country to their holiday destinations, for example Italy. And to do that, it highlights all the big highways and motorways, and it ignores pretty much all other information. It's got some cities on there, maybe some symbols for things related to traffic, but it has very little relationship to the physical reality other than the road network. And if you think of the scale, this map is 800 kilometers wide, and so each individual road would easily be hundreds of meters wide, and I've never seen such a big road. and these things with the purple ones would probably even be kilometers wide, and it's instead the purple just indicates whether or not a road is recommended to use. So this map is a poor representation of physical reality of what the land surface looks like. If you wanted to know the width of individual roads, this map would be completely useless. But for its intended purpose, driving from the Netherlands to Italy or to Switzerland, it's really good. It's a very simple, clear map which shows people what they need to know, but nothing more. So in this case, it's perfectly good. So errors in spatial data. Where do these errors come from? Well, some data errors, they occur when we capture the data. So when we record the data, we can misrecord it. We can write down some property wrong. We can write down the wrong location. We can have an error in the GPS. The GPS might give us the wrong location. If we're using satellite data, there might be a problem with the sensor. There might be clouds obscuring our area of interest. But also aging, the land surface and the human structures, the buildings, the houses, and it's all continuously changing. So a map from a couple of years ago might no longer accurately represent the world that we live in today. There are also, as we represent things, we might simplify things a little bit too much. If the road map we looked at previously is perfectly good for driving, at least driving from one country to another. However, to actually find your hotel, it's probably not good enough. Doesn't have enough detail to find your hotel. And if we wanted to use this map for, say, a study of ecosystems, and we wanted to know where individual forests are located and how wide these forests are and what kind of trees grow in these forests, this map is completely inadequate. And then lastly, some data can be lost in the GIS operations. As we process our maps, we can lose some data. For example, we can classify the data, which will lose some information. Or as we do calculations, then rounding errors in the numbers can lead to errors or at least a loss of data. Does the error matter? Sometimes it does and sometimes it doesn't. It really depends on whether the data is still fit for purpose. Here you see the locations of mine entries as recorded by the Coal Authority. In the Coal Authority, they use all these historical maps to find all these locations of old mining. And this is relevant because as we are building houses on top of there, or we have already built houses on top of this, then if these coal mines, if they still exist in the subsurface, and if they were to collapse, then that's going to affect the buildings on top of it. Well, on the bottom you see a picture of a sinkhole that forms as a consequence of a mine tunnel collapsing. So yeah, it's very important. If you buy a house, you don't want to buy a house on top of a mine tunnel. But the data sources that the Coal Authority used, yeah, there are all these old maps of most of the mining, for example, in Glasgow, happened a long time ago, so I would say 150 years ago or more. So yeah, the maps in those days were, how good were those maps? They didn't have satellite images, they didn't have aerial photographs to make maps, so you can imagine that there could be errors in there, that the maps back then were not as good as they are now. They didn't have GPS to determine their location, so they would have made errors in determining the locations of the mine entries. So there's all these potential sources of errors, and of course digitization errors by the Coal Authority, that we don't know exactly where those mine entries are. And that's why if you buy a house, then the Coal Authority, they do a check for you, for your solicitor, and they check if there's a mine entry mapped within 50 meters. So that's really to compensate for this error. They don't tell you exactly there is guaranteed to be an old mine under your house, but if there's anything within 50 meters, which is probably their sort of model for their typical error, then you know you need to be worried, and this report will be given to your solicitor, it will be given to your bank, so that can affect the decisions being made when you buy a house. So does the error matter? Well, it depends on a number of things. It depends on scale. If your problem deals with issues on a kilometer scale and your error is in the centimeter or meter scale, your error probably doesn't matter. If your error propagates through your GIS system and just starts small but has a big impact, then it does matter. And lastly, GIS is just a model, and models are always limited in how complex they can be. We try to make our models as simple as possible, but just not too simple. So no matter is ever 100% right. But ignoring error can lead to serious problems. It can allow you to select the wrong locations. It can allow you to detect patterns which aren't really there. You see patterns in your data, but they don't exist in the real world. It could allow you to draw wrong conclusions, find relationships that matter or don't find them. And most importantly, it can lead to poor decisions, which cost a lot of money and possibly lives. So typically we distinguish between 3 types of error. There's the gross error, the systematic error, and the random error. And I'll just walk over those issues to explain what they are. Gross errors are really big errors, and it's a value which is often very obviously wrong. Here you see a map, and this map is basically a recording of GPS locations. Google Maps can save wherever you've been, and as you can see, I started here in the town of Green River. We went to the coffee shop, did some work there, and then we drove. But somehow we drove from Green River to Moab in Utah, but somehow Google or the GPS thought we drove through a different state, and we went back again. And Google thinks that we drove, what does it say? Almost 400 miles in 46 minutes. Well, that is rather fast. And we definitely didn't do that. But we did drive around some canyons over here along the river Colorado. It's got these very deep canyons. So quite possibly that caused some errors in the GPS. So it's a gross error. An error which is caused by a problem with the instruments. And it's so wrong that it's typically easy to spot. There are also consistent errors. Often it's an instrument which isn't properly calibrated. We calibrate instruments to fix consistent errors. If you have a thermometer and your thermometer says 42 degrees, whereas you know that your reference object is 45 degrees, then you can calibrate it simply saying, okay, we need to adjust these measurements like this. So a systematic error is consistent. It's always the same. For example, this tractor here, it's got the GPS antenna on a stake in front of the tractor. So we always know the position is always, maybe say, a meter in front of the tractor. So it's consistent, which means that we can correct for it. We can just add or subtract this consistent value, and then we can get really close to the real value simply by correcting our measurements. And then random errors. Basically, it's errors after we've corrected all the systematic errors in our measurement device or our GPS or our sensors. Then there are still some errors left, and there's pretty much, if they're random, then there's often sort of nicely scattered around the true value, which has the nice advantage that if you take the average of this, then the average value will be really close to the true value. So if you have a proper random error, that's okay. Just take multiple measurements and then take the average. So we have different types of errors in spatial data. There's errors in the positioning, which can be, for example, GPS has typically an error of about 10 meters. Much better if you buy a survey grade RTK or DGPS. If you're using a map to determine where you are, you probably have an even bigger error. There's errors in the values that we ascribe, the attributes that we record at these positions. Places change over time, so if we're in the wrong, if we misjudge the time, then we can often use the wrong map, a map that's out of date, for example. Spatial data can be missing, might not be complete. And lastly, there's sort of logical consistency. For example, if you have two neighborhoods, but and you draw a polygon for both spaces, so let's say we have a neighborhood here and a neighborhood here, but there's a little bit of space between them. That's a topology error, because this space probably shouldn't be there. This is error space. Scale of a map can also affect the results of our analysis. On the left hand side you see a low resolution map of 1:25,000, and on the right hand side you see the same area of woodland mapped on 1:10,000. And as you can see, there's much more detail in this 1:10,000 map. This area, for example, isn't on the lower resolution map. This thing is missing. It has some serious consequences. Our low resolution area has a larger area than our high resolution map, and the perimeter in our high resolution is much longer than in our low resolution. So the scale of the data can affect the values that we obtain. And it's also important to stress the difference between accuracy and precision. Accuracy is how close you are to the true value. So really how representative your data is for the true value, whereas precision is more a matter of how precise you record it, how many decimal places you use. So they're not necessarily the same. Ideally, we use precision, which is appropriate for the accuracy we have. If we're using a GPS for our location to measure a distance, then we know that there's an error going to be in there for at least 10 meters. So there's no point in writing down this distance in centimeters. So precision and accuracy, they're different things, but they are related. Precisional accuracy can also affect types of geographic analysis. For example, if you want to know how many circles, how many points are in this rectangle, then we can count that. But what if there is some uncertainty? If these are GPS points, then this point could actually also be on the outside, and this point here could actually be on the inside. So there is definitely some uncertainty there, and we can accommodate for this. Right now we have 14 points inside and 20 points outside of the rectangle. But if we consider that our rectangle might have a positional accuracy of 100 meters, then actually suddenly things change, and we could have a smallest case scenario where we're only counting these points within this smallest rectangle. We can have sort of average scenario, which we're probably using the original rectangle, or a sort of maximum case where we're using a bigger rectangle, 100 meter bigger rectangle. So there's uncertainty caused in your analysis as well by uncertainties in your position of your input features. So we have 11 points which are definitely inside our rectangle, and we have 16 points which are definitely out. But there are also 7 points like this one and this one and this one, where we're not entirely sure if it's going to be inside or outside the rectangle if we account for this positional accuracy. Then there's also the modifiable aerial unit problem, which is basically that where we draw our sampling areas can affect how we perceive the world and how we obtain measurements, statistical measurements from our data. So in the top figure we have these red dots here, red dots, we have blue dots over here, and then more red dots. If we just take the whole rectangle as our measurement device, then we have roughly the same amount of blue dots and red dots. So I visualized that by drawing this whole rectangle lilac. We could do some kind of optimal thing where we try to separate the red and the blue points, and we can get a shape more like this. Now this is pure, the center, this is purely blue, and this is purely red and purely red. We can draw a grid over it. It's in the third picture. And if my grid happens to coincide with the subdivision in the data, then it actually shows it really nicely. However, if my grid doesn't quite coincide with the distribution of the points, because I start seeing mixing effects. So the sub areas that we use to analyze this are data points. For example, this could be census areas, this could be NHS health board areas. They affect how we the statistical descriptors that we get for our areas. Scale of the data can also affect how we perceive the data on our map. If you look at the bottom map, we have a political map of the US, of probably voting results or election results. And if you look at this at the scale of the lower image, then we're basically seeing blue states and we're seeing red states. And we'd be inclined to think that everybody in California is voting for the Democrats, and everybody in say Utah votes for the Republicans. The last thing is true, but California, if we look in more detail, we can see that there's actually Democrat voting areas in California, but there's also areas where most people vote Republican. So if you look at more detail, then actually the world is a bit more complicated, and this can affect how we can analyze our data and what kind of conclusions that we should draw from it. Errors don't just exist in our input parameters. As we do analyses in GIS, if we do calculations with our data, then our initial errors are taken, and they could be they're affecting our calculations, and they're affecting our output parameters. So what impact does this have? Well, we can only study this by considering this. So if what effect do our errors have? And ideally you do a sensitivity analysis. So you vary your input parameters in the sort of range that you'd expect any errors to be, and then you observe the effect that this has on your output parameters. And you can maybe plot a graph of variation in input parameters versus variation in output parameters, and then see if there's any clear relationship, and see if this error, if the sensitivity to the error is big enough to cause problems for your analysis. Does it affect your real conclusions? So how do we deal with errors in GIS? What's the best way to work with errors and accept that they can occur, but how do we minimize them from having an input on our conclusions? Well, we should always check our data. If we put garbage into our analysis, or if our input parameters are wrong, we'll get garbage out. We'll get wrong conclusions out. So garbage in is garbage out. So make sure your input data are good and that they are what you expect them to be. If we're using a map, for example, the political map that we just looked at, then yeah, every polygon, it might be represented as a homogeneous mass, but there might be all kinds of heterogeneity at a smaller scale. This is not just political phenomena, all kinds of natural phenomena are much more complicated at a finer scale than at the scale of the map that we use to represent these features. The boundaries that we draw between things, especially if we're using a vector view of the world, we'll be using sharp boundaries. Not all boundaries are sharp. Many things change gradually from one value to another. And then we need to decide whether vectors or rasters are the best choice to represent these features. The scale and the resolution can affect our outcomes, and how our data is generalized, how we put it on the map, how we simplify it, can also affect our conclusions. So in conclusion, GIS models, they have a finite accuracy. GIS is they're it's a model, and models, a good model should be as simple as possible, but just not too simple. So every model is basically wrong as long as you find enough detail that it's wrong, but it's good enough for its intended purpose. So if we're dealing with errors, we've looked at gross errors, which are very wrong and often easy to spot. Systematic errors, where the error is consistent and we can correct for it. So for example, an instrument which isn't properly calibrated. And we've looked at random errors, so the errors that are left after all systematic errors have been fixed and gross errors have been picked out because they were so obviously wrong. That leaves the random errors. And the good thing, if you take multiple measurements and you average them, then the average of the random errors should basically get very close to the true value. A published map isn't necessarily a picture of the truth. It's people who made these maps were also dealing with time constraints and limitations. They might have had a different thing in mind than what you are looking for. The way we represent our data can introduce errors. So the scale, how we draw boundaries, how we simplify our data. All of this can affect our end results and cause errors. And the best way to deal with this is to analyze how sensitive your analysis is to GIS. Make small variations in your input parameters and see how the output parameters are affected by this.